Hello everyone. Welcome to this CAIDA talk. It's my pleasure to welcome Professor Saeed Ghadimi to be a speaker in our series. Saeed is an assistant professor in the Department of Management Science at the University of Waterloo. Before joining Waterloo, he was an associate research scholar at Princeton, and he also received his PhD with a major in industrial and systems engineering and a minor in mathematics from University of Florida. His research is mainly focused on decision-making under uncertainty, in particular reinforcement learning and stochastic optimization, developing first-order and second-order algorithms for data analytics and large-scale optimization, simulation-based optimization, and computational lower bounds. And today, Saeed will speak to us about non-convex stochastic nested optimization. So thanks a lot for being here, Saeed. Welcome. Just to the audience, please feel free to have your questions, raise your hand to ask questions or have your questions on the chat. Okay, I'll go on mute.
Okay, thanks, Mariam, for the introduction. Thanks for the invitation. It's a pleasure to be with all of you here virtually. So as Maria mentioned, today I'm going to talk about a non-classical stochastic optimization problem, specifically a stochastic nested optimization problem. So in particular, I'm interested in solving a composition function, a composition problem that you want to minimize a function f of x, which is a composition of two or more functions over a convex feasible set, convex and closed feasible set. So here, if all of these fi's are deterministic functions, then it's just a classical nonlinear deterministic optimization problem. Or if just the outer function f1 is a stochastic function, meaning that we don't have access to its exact information, such as the function values or the gradients of the objective function, then it is still a classical stochastic optimization. But if any of these inner functions is a stochastic and the outer functions is not linear, then the objective function is not a classical stochastic optimization in the sense that even if you have an unbiased estimator, for example, for the gradient of each fi, then you cannot have an unbiased estimator for the gradient of the whole function. Actually, there is a way to get an unbiased estimator, as I will mention in the next slides. However, the variance of that estimator polynomial, it depends on the problem dimension, and so it's not practical to use that approach if you have a larger scale optimization problem. So more formally here, I assume that we don't have exact information for all functions fi. Some can be deterministic and we have exact information. This is the general case. And in particular, we assume that each fi is given as expectation of a function gi. And we assume that we can query this expectation and get its unbiased estimator and unbiased estimator for its gradient, just a classical assumption in the stochastic optimization. Now let's first see some settings that we can identify these nested problems. So the first one is sparse additive models. So we have a sample data points xi and yi, and we assume that yi is given as a summation of some feature vectors plus some noise. So assuming that you have some pre-specified functional space hj for each feature function hj, so the goal is to estimate the feature functions by minimizing this objective function. So here, the first term is a linear term in terms of the expectation. So this is the expectation of this error squared plus this regularization term here, which, as you can see, we have a root function here, the square root function here. And so this would be a composition of a nonlinear function and an expectation. So this is an example of this nested structure that we have. So the point here is, if you just apply the stochastic gradient descent, you cannot ensure the convergence rate because you don't have the unbiased estimator and you don't know how the bias terms or the variance of your estimator are bounded. The next problem is the policy evaluation for Markov decision processes. So assume that you have a Markov chain, x0, x1, and so on, and you have an unknown transition operator P and a reward function R. So the goal is to estimate the value function, which is given as the expectation of the total reward. Here, gamma is just a discount reward factor. So we want to estimate this value function. So if you write down this one as a vector equations, then we have the Bellman equations. V equals R plus gamma times PV. So if size of P is large, and if we don't know P, we cannot solve these equations exactly. Instead, we can estimate the solution. So assume that we can sketch, we have a sketching matrix S of P and a linear model for the value function. So assume that the value function is given as a linear combination of some basis function. So here, assuming that phi is the matrix with columns being this basis function and P had be a sample transition matrix, because we don't know the exact transition matrix, then instead of solving the Bellman equation, we can minimize these residuals. So this is a sketching matrix times this quantity. So here, as you can see, we have the S-squared norm as the outer function and a nonlinear function, and we have the expectation inside this nonlinear function. So we have the nested structure here. If you have an unbiased estimator for P hat, it doesn't give you an unbiased estimator for the objective function. The next one is low rank matrix estimation. So assume that X bar is an unknown matrix and we want to approximate it. One can sample from the unknown matrix, and each sample returns an unbiased estimator such that the expectation of X would be X bar. Now, assuming that K is less than D, a pre-specified rank, the low rank matrix estimation is minimizing this function. So here L is a loss function, and this is the difference between the expectation of X and U times V transpose, in which U and V are D times K matrices. So here again, this L function, usually, for example, it can be the Frobenius norm or any nonlinear function. And we have the expectation inside the nonlinear function. So again, unbiased estimator for X does not give you an unbiased estimator for the objective function. So you cannot apply the classical stochastic approximation algorithm to solve this problem. The next one is minimax problems. So assume that you have the stochastic games with random payoffs. So in this case, we want to solve this minimax problem. Here, the max operator can be seen as the outer function, and this would be the inner function. And this max function is not a linear function in the sense that, so actually it's not a smooth function here. So here we are assuming that the objective functions, and as I will mention, the next slides are smooth. The max, as we know, is not a smooth function, but for example, we can use there are several approximation for the max function, like the softmax or a few other approximation which makes this max function a smooth function. And then we have a minimization of a nested problem, and then we want to minimize the objective function. Again, it will be the nested structure. The next example is risk-averse stochastic optimization. So you want to minimize the semi-deviation risk functions. So you want to minimize this objective function. So here, the first term is linear in terms of the expectation, but the second term, as you can see, there is a nonlinearity here. So we have the expectation, and there is a composition of a nonlinear function and that expectation. The next one is the multi-stage stochastic optimization. So if in the multi-stage stochastic optimization, the random variables psi, assume that for each stage we have psi I, if we assume that these random variables are coming from a finite random walk process, then the multi-stage stochastic optimization can be written in this form. So for each stage, it just depends on the previous. So we have just conditional expectation of psi2 given psi1 and psi2 given psi t minus 1. So we can consider each of these inner minimization problem as an inner function. And then we have a nested structure for more than two or more than function. And the last example is compressed sensing. So assume that X star be an unknown signal that we wish to recover, and we are allowed to observe measurements of the form, for example, Y equals A transpose X star plus some noise. So the classical formulation is we want to minimize the expectation of this error, Y minus A transpose X squared, assuming that we just have, for example, K, X, the norm 0 of X is bounded by K. So in general, one could run the standard stochastic gradient algorithm for n iterations with single samples in each iteration. And without further assumptions on the optimal signal, we know that we need, if there is no sparsity, we need approximately these samples to accurately estimate X star. For the sparse case, we know that we need K times log D samples for accurate reconstruction of the optimal signal. However, recently, motivated by the success of deep learning, people have proposed a generative approach to compressed sensing. In this case, we assume that there is a latent signal vector Z star, and we assume that G, which is a neural net, assume that that's a function, the output would be from Rk to Rd, which K is much less than D. Then we assume that the true signal would be the output of this neural net G. So we have a latent Z star, G of Z star would be X star. So again, here we assume that we are allowed to observe the measurement of A transpose times G plus noise. In this case, the optimization problem would be the expectation of Y minus A transpose G of Z squared. So this G is no longer a linear term here. So it is assumed to be a deep neural network with depths T, for example. Sorry. So we assume that G is a composition of T functions. And so in this case, each function here can be the expectation of sigma of, for example, G transpose Y minus B, which here in sigma would be the activation function. And G and B belongs to the RD plus 1, and then this probability Pi and Jij would be a distribution over the weight and the bias at each layer of the neural net. So we know that the statistical complexity of this formulation tells us that we need K samples to accurately reconstruct the optimal signal. However, we don't know how to efficiently solve this optimization problem because it's no longer a classical stochastic optimization problem because of this G. Specifically, if you have several layers, in the case of the deep learning, then it's hard to just apply the stochastic gradient to solve this problem. So now the question is how we solve these nested stochastic optimization problems. So for the rest of the talk, I first review some related works, then I will talk about the algorithm for solving the two-level case that we just have a composition of two functions. And then I will talk about the generalization of that algorithm to the multi-level case that we have more than two functions. For example, in that risk-averse function, we have a composition of three functions, or in the multi-stage or in deep neural net, usually we have more than two functions in terms of the nested structure. So interest in the stochastic approximation algorithm for solving these nested structure problems, it seems that it dates back to 1976, where for a function, for a problem with the stochastic constraint, people have used penalty term in the objective function. For example, you have a stochastic constraint, and then you use, for example, norm squared of penalized, and you use the norm squared of that constraint in the objective function and then penalize that one. So in this case, you have a nested structure. However, the main approach in the literature was to use 2 or multiple level stochastic recursive algorithms in different time scales. For example, for the 2-level case, 2 step-size sequences were used, one for updating the main decision variable and another for filtering the value of the inner function. Because when you have a composition of, for example, 2 functions, you also need to estimate the value of the inner function, since you want to estimate the gradient of the outer function at that inner function. So instead of, in addition to the decision variable x, you also need to estimate the value of the inner function at that point x. So for those algorithms, the key point is that the outer method must be infinitely slower than the inner one. And in this case, we have a decrease in the convergence rate, and we cannot recover the convergence rate for the single-level classical stochastic optimization problems. So recently, people have studied this nested structure in the sense of finite time convergence. For example, there are several works recently which shows the convergence of, which proposed some algorithms to solve the nested problems, but under different convexity assumptions of the objective function. However, all of the convergence results are worse than the counterparts for the single-level problems. There is another work recently showing that for the central limit theorem, the case is different. While for these algorithms, we cannot recover their convergence rate for the single-level problem, for the central limit theorem, people have shown that the d-sample empirical optimal value of the problem converges to the true optimal value at the rate of 1 over square root of d. And we know that this is the same for the single-level problems. So no matter of how many functions you have as a composition or in the nested structure, we can establish, people have shown that you can establish the central limit theorem with the same convergence rate. So this motivates us to look for some algorithms that can recover the convergence rate that we have for the single-level problem, even if we have a nested structure. So as I mentioned in the first slide, there is a work showing that by using some techniques, we can get unbiased estimator for the gradient of this nested function. However, the variance of that estimator polynomially depends on the problem dimension, and that appears in the convergence rate. So for larger scale problems, then I don't remember exactly the dependence, maybe d, at least it was d cubed, if I remember correctly. So for the larger scale problems, then you have a large constant for the upper bound that you have in your convergence result. And so theoretically, the algorithm does not converge unless you run it for so many iterations. So as I mentioned, now the question is it possible to get the same convergence rate for this nested structure, this nested optimization problem, regardless of the number of levels or layers, which is shown by t in our notation here. So if t is 1, then we have a classical stochastic optimization. If t is greater than 1, people have developed some algorithms and got the convergence rate, but all of them are worse than the counterparts when t equals 1. So in this talk, I want to answer this question. Okay, so feel free to ask questions and stop me whenever you have any question. So let's first see the simple case, the 2-level case. So here, the objective function is given as a composition of 2 functions. For simplicity, just f of g of x. So the main idea here is, instead of just looking for x, we are lifting the problem into a higher dimensional space. So instead of just looking for the decision variable x, we also look for the gradient of f at x and the value of g at this point x. So the output of the algorithm would be x, estimator for the gradient of f, and estimator for the value of g at x. So here is our first algorithm for the two-level case. So at the beginning, at each step, we just solve a quadratic subproblem. And then in the next step, we take the convex combination of all of the solutions to the subproblems. And here in the linear term in this subproblem, this zk, would be just the weighted average of the stochastic gradients. And we also have another sequence u, which records the weighted average of the inner function value. So just this g is the estimation for the inner function values for little g. So again, so we just solve a subproblem. We take the convex combination of all of these solutions to the subproblem. We use the weighted average of all stochastic gradients inside the subproblem, and we also use, it actually calculates the weighted average of all stochastic values of the inner function. And the output of this algorithm would be XR, ZR, and actually we can just consider UR as estimation for the inner function values. So here, this R is a random index. So as you know, unlike the convex optimization, in the stochastic non-convex optimization, there is no approach to establish the convergence rate, for example, for the last iterator of the algorithm, or for example, the convex combination of all generated solutions, as we have for the convex case. The current practice for the non-convex stochastic optimization is to just not necessarily uniformly, to just randomly pick one of the generated solutions. And the probability distribution of this index R depends on the choice of the step size that you have. But usually, if your step size is constant, this would be just a uniform distribution. So you run the algorithm for capital N iterations, and the output would be a solution whose index is chosen randomly from 1 to n. In this case, we can establish the convergence rate for that random index. So here we make just a common assumption in the stochastic optimization for each function f and g. So we assume that we have unbiased estimator for the function values of g, unbiased estimator for the gradient of g and gradient of f, and we assume that their variance or their second moments are bounded. The point here is, as you can see here, this is not g of xk plus 1, it's uk, because we don't know the exact value of the g. So we just estimate the value of g with uk as we had here. So this uk is an estimation for the value of g. And at each iteration, we just calculate the gradient of f at uk. And this is one of the main difficulty for the nested structure, because if you were able to calculate this one at g, then you will have an unbiased estimator, and you can just apply the gradient descent to solve the problem.
Oh, there's just one question on the chat about the algorithm one.
What the value of g and j? Yeah. Okay. So here, this is the g. G would be an unbiased estimator for the value of the inner function, and j would be an unbiased estimator for the Jacobian of g, and s would be an unbiased estimator for the gradient of f at some point uk. So this is a nested problem. So the gradient of f of g of x would be g of x Jacobian of g of x transpose times the gradient of f. So this is the Jacobian transpose, and this is estimation for the gradient of f. So this would be an estimator for the gradient of f. However, it is a bias estimator for the gradient of f at xk plus 1. So here, since we have a composition structure, it will be hard to assume that we have, you're welcome. It's hard to assume that we have a convexity property for the whole functions because that's what matters. So here we just focus on the non-convex case. So we don't care it is convex or non-convex because when you have a composition of several functions, it's very likely that you get a non-convex function. So in this case, we know that the optimality function, the optimality condition would be x hat would be a local mean if the negative gradient of f belongs to the normal cone at x hat. This is related to the subproblem that we solve. So this is the subproblem that we solve at each iteration, the quadratic subproblem. So this condition here, we can use this condition to satisfy this condition. Indeed, for this z, if we say that negative z belongs to the normal cone of x, this means that the solution x here equals to the solution of the subproblem. So if this z is just the gradient of f at x, then this x would be a local mean of the function. So by using this observation, we can define our measure for the violation of the optimality condition. So we have two terms here. So our measure would be this v of x and z. So the first term would be the difference between x and y bar, and the second would be the difference between z and the gradient of f at x. So if z equals gradient of f at x, this one would be 0, and then we just have this one. And if negative z belongs to a normal cone, this term will be also 0. So if x is a local mean, then the value of this one would be 0, the value of v. So for example, for the unconstrained case, y bar minus x would be just z, and this v would be just z squared plus norm of z minus gradient of f squared. So this is just an upper bound for the size of the gradient. So if the problem is unconstrained, this v would be an upper bound on the size of the gradient squared. And if it is a constraint, still it would be a measure on the distance to the local mean. So here, since we cannot recover the exact local mean, the epsilon and an epsilon stationary point would be a point. So here we just don't have x, it's x and z. So an epsilon stationary pair of x and z would be a point such that the expectation of the square root of v of x and z is bounded by epsilon. So we are looking for a solution that satisfies this condition. So there is a solution, there's a question in the chat. Is the gradient in the normal cone sufficient for local mean in the interior of the constraint set if the objective function is non-convex? Couldn't have a saddle point. Yes. So essentially, if the gradient is 0 on the interior of the objective function on the interior of the feasible set, then you get the stationary point. Yeah, here I need to be more accurate. Essentially, by this one, when you make that gradient 0, you find a stationary point, not necessarily a local mean. So here, as you can see, so in our subproblem, there is a step size beta, but in our optimality measure, we set beta equals 1, and we can just easily show that the difference between y bar and x, if beta is set to 1, is bounded by max of 1 and beta times this difference when beta is just any positive number. So now let's see how our measure of optimality is related to the measures that have been used in the literature. So here I have listed two famous optimality measures. The first one is the proximal point mapping. So assume that y bar is a solution to this one. The measure of optimality for this proximal point would be just y bar minus x squared. So if you define z hat to be the gradient of f at this point, then we can easily see that this optimality measure is bounded by our optimality measure, and it is also bounded by this constant times this optimality measure. The next one is the gradient mapping, which instead of this f, we have the gradient of f of x. In this case, if you choose z tilde to be the gradient of f at x, then the termination criterion for the gradient mapping equals our termination criterion by this choice of z tilde. However, under a stochastic setting, we cannot calculate this z tilde and this z bar because it's just gradient of f at y bar or x, and we don't know the gradient of objective function. However, in our case, we can calculate the zk. So zk would be an online certificate for the value of the gradient of the objective function. As I mentioned earlier, the output of our algorithm is not just an estimator for the decision variable, but we also have the estimator for the gradient of the objective function and the value of the inner function at the solution that we get for the problem, essentially as an approximate stationary point. So here are just some assumptions and technical results. So to establish the convergence rate of our algorithm, the nested average stochastic approximations, or in summary, just NASA, we assume that f and g and their derivatives are Lipschitz continuous. And under this condition, we can show that the objective function is Lipschitz continuous. And we can also show that regardless of this assumption, the optimal value of the subproblem is also, its gradient is Lipschitz continuous. So here is the main convergence result for the NASA method. So if the beta k is just set to a constant number, depending on the problem parameters, and tau k is just 1 over a square root of n, so here n is the total number of iterations, then we can show that the total sample complexity of our method is in the order of 1 over epsilon to 4 to find an epsilon stationary point of the problem. And this is the same sample complexity to estimate, to find a solution such that the value of g at that solution and u, which is an estimation for the inner function, is bounded by epsilon. So here we use the same, if I go back to the algorithm. So as you can see, so here in the algorithm, we set a and b to 1. So this is just 1 minus tau k, 1 minus tau k. And so we are, and here we also have 1 minus tau k for xk. So we are just using a single time scale for in the algorithm. And so because of this, we can establish the same convergence result for the, for example, for the unconstrained case, the gradient of the objective function and the value of the inner function. And in the case of the constrained case, for the convergence of the V that we had. So now let's compare this result to the existing one. So the best complexity bound for the nested problem was 1 over epsilon to 4.5. So this was for the unconstrained case. However, our complexity bound, which is 1 over epsilon to 4, matches the sample complexity for the single level problem. And recently people have shown that this 1 over epsilon to 4 is unimprovable for the single level problems. So if you just want to minimize an expected function, then you need at least 1 over epsilon to 4 samples to find an epsilon stationary point of the problem. It is also consistent with the central limit theorem that I mentioned at the beginning. So if you remember, for this theorem, people have shown that there is no difference if you just have one function or a composition of two or more functions. You get the same convergence rate for the central limit theorem. And here we show that if you have two functions, we can still get the same convergence rate as the single level problem. And the last point is the convergence rate of this method is the same for both constraint and unconstrained problems. So one common practice for the constraint non-convex stochastic optimization is to take a batch of samples per iterations to reduce the noise associated with the stochastic gradient. For the unconstrained case, you don't need it, but a common practice for the constraint case was to use a batch of samples per iterations. However, this method does not need any batch of samples if the problem happens to be constrained. And this is the asymptotic rate of convergence for the algorithm. So if tau k satisfies these two conditions, and assuming that x star, z star, and u star are the limit points of xk, zk, and uk, then u star would be the value of g at x star, z star would be the gradient of the objective function at x star, and negative z star belongs to the normal cone. So here I just briefly explain the sketch of the proof. So to show the convergence rate of this algorithm, we need to define a merit function. So here we have three terms. The first one is the optimality gap. The second one is the solution, the optimal solution to the subproblem. And the third term would be the error in estimating the inner function values. So we can easily see that the optimal value of the subproblem would be negative. So this term would be positive, and actually this one, this function W would be positive. Then we show that by properly choosing the step size beta k, we can get this recursion. So wk plus 1 minus wk is bounded by this term. Here rk is an error which is fk measurable. By showing this one and summing up all of those inequalities, we can get this inequality. So the first term here is the first term that we use for the optimality measure. And similar to this one, we can show that the second term, which is the difference between the gradient of f at x and zk, is also bounded by a constant which is in the same order of this constant. And then you divide both sides by the summation of tau k, and then we get the rate of convergence for the NASA method. Now let's see a special case that the inner function is just a linear function. In this case, we just have a classical stochastic optimization problem. So we can simplify the algorithm. We still have the subproblem. We still have the convex combination of the solutions to the subproblem, the convex combination of the stochastic gradients. However, here we just have the gradient at xk, the stochastic gradient at xk plus 1. There is no Jacobian here, it's actually identity. And there is no need to have a sequence uk to track the value of the inner function because it's a deterministic function and we know the function value. So similarly, we can show the same convergence rate for this algorithm for the single level problem and recover 1 over epsilon to 4 complexity bound. And if we assume that the second moment is bounded, then this algorithm is actually parameter free in the sense that we can just set the step size policy beta k to any positive constant. And there is no condition on beta. And as I mentioned, we get the same complexity bound. However, if you make a weaker assumption, and instead of the second moment of instead of assuming that the second moment of the stochastic gradient is bounded, if you assume that only the variance is bounded, we still get the same complexity bound, but the choice of beta depends on the problem parameters. So in the remaining time, I want to talk about the generalization to the multi-level case. What happens if we have more than two functions? In this case, direct generalization of the NASA method does not converge due to the accumulated error in estimating the inner function values. So for the two-level case, we just have one inner function, and we can handle the errors associated with estimating that inner function. However, this is not the case when you have more than two functions. In this case, for the direct generalization, we need a mini batch of samples to reduce the noise associated in that estimation of the inner function values. In this case, we can still get the convergence rate, but we get something worse than 1 over epsilon to 4. Essentially, we get 1 over to epsilon to 6, but there is a way to fix that one and still get 1 over epsilon to 4 that I now just briefly explain it. So this is the direct generalization of the NASA method to the multi-level case. We still have a sub-problem, it's the same. We still have the convex combination of the solutions to the sub-problem. We still have the convex combination of the stochastic gradients. So here, if T is 2, we just have a multiplication of 2 matrices. Here we have T matrices. And this would be the weighted average of the stochastic gradients. And we have the weighted average of the inner function values. But instead of one function values, we have essentially T function values. So here we have W1 through WT to estimate the inner function values. So here in the NASA for the two-level case, this was just G. But here, as you can see, it is G bar. So we need to take a batch of samples to reduce the noise associated with the estimating of the inner function values. Otherwise, this algorithm does not converge. So here, this algorithm, if T equals to 2 and BK equals 1, so remember that BK is the number of samples that we take as the mini batch size at each iteration. If BK is 1, T is 2, this is just the NASA for the two-level case. So to establish the convergence rate of this algorithm, we need to make the assumptions about these stochastic values that we get from the stochastic oracle. So we make the same assumptions. We assume that the expectation of the Jacobians is the expectation of the GK would be the Jacobians, and the variance of the function evaluations is bounded, and the expectation of GI is just FI. And the second moment of the Jacobian is bounded. We also assume that given FK is our filter up to iteration K, the outputs of the stochastic oracle at each level I are independent of each other. So we calculate the stochastic values for function, for example, Fi, and then the values of the output of the oracle for Fj is independent of Fi on the same iteration. So here again, we just assume that the functions Fi and their derivatives are Lipschitz continuous. And we can show that under this assumption, when we have more than two functions, the overall objective function is also Lipschitz continuous. So here is the convergence rate for this algorithm. So beta k is still a constant, tau k is still 1 over square root of n, but bk, the batch size per iteration, is 1 over tau k. Essentially, it is a square root of n. So this means that to find an epsilon stationary pair of the problem, we need 1 over epsilon squared samples per iterations, and the total sample complexity would be 1 over epsilon to 6. So essentially, the total number of iterations would be 1 over epsilon to 4. We need 1 over epsilon squared for the samples per iterations, and the total sample complexity would be 1 over epsilon to 6. So this rho to power t, essentially this rho depends on the Lipschitz constant and the variance of the inner functions. And we just have t to power 6. So for this complexity bound, there is no relation between t and epsilon. As we will see, there was a relation in the existing algorithms. And again, this is the same complexity bound to estimate the value of the inner functions, similar to what we have for the two-level case. However, instead of 1 over epsilon to 4, we get 1 over epsilon to 6. So the best bound for this one was 1 over epsilon to 7 plus t divided by 2. As you can see here, the complexity bound depends on epsilon and t, and by increasing t, you will exponentially increase epsilon. But in our complexity bound, however, it is worse than 1 over epsilon to 4, there is no direct dependency between t and epsilon. The power of epsilon here is fixed. However, you need batch of samples per iterations. So in the next few minutes, I just discussed another algorithm that relaxes the need to take a batch of samples per iterations. So this algorithm is same as the previous algorithm. As again, you just have a subproblem, you take the convex combination of the solution to the subproblem, convex combination of the stochastic gradients. But here, instead of taking the convex combination of the stochastic function values, you take the convex combination of the stochastic function value. This is just GI, not G bar, one sample, but we add this linearization term here. So the difference between this algorithm and the previous one is that instead of having G bar here and taking a batch of samples per iteration, we just take one sample and take this convex combination and add this linearization term here. And this will help us to reduce the noise associated with the value of the inner function at each iterations and removes the necessity to take a batch of samples per iteration. So here is the convergence result of this algorithm. Again, beta k is just a constant number. Tau k is just 1 over square root of n. And we get 1 over epsilon to 4 complexity bound for this algorithm under the same assumptions. So I have not changed any assumptions. But by just adding this term, we can show that we can get 1 over epsilon to 4 convergence rate, and this is the same complexity bound to estimate the inner function values. And as I mentioned, this is the same bound for the single level stochastic optimization problem, and people have recently shown that it is unimprovable for the stochastic non-convex problems. So essentially, this algorithm tells us that no matter of how many functions you have in the objective function in the composition form, you still get the same convergence rate if you can properly handle the noise associated with the estimating the inner function values. This is the key point in this algorithm. So there is another work, recent work by Andrzej Rosinski, which obtains the same complexity bound for the multi-level case, but to obtain that complexity bound, you need to assume that the feasible set is bounded. So the convergence analysis does not apply to the unconstrained case. And again, this one, similar to the NASA method for the two-level case, we have the same analysis for the constrained and unconstrained cases. So again, we don't need a batch of samples per iterations, even if the problem happens to be constrained. So I just need to mention another work which has been recently proposed for the multi-level case, but under a stronger assumption. So the method by Zhang and Xiao achieved a sample complexity of 1/epsilon cube. However, this epsilon cube is obtained under a stronger assumption than the usual assumption that we make for the classical stochastic optimization problem. Essentially, they need to assume that mean squared Lipschitz smoothness of the individual functions fi and their gradients. So we do not make the assumption on the smoothness of each stochastic function. We just assume that the expectation of that function is smooth. And they also need to assume that for a fixed batch of samples, one could query the oracle on different points. So you can fix the sample and then query the oracle at different points, but this is not suited for the general online setting of the stochastic optimization, that you just receive the samples one by one and you have no control over the samples. And they also need to take a batch of samples, but the order of this sample would be t cube. So if you have moderately large values of t, it would be hard to implement this algorithm because you need a large portion of samples per iterations. However, in practice, usually you need less number of samples. But even in the classical stochastic optimization, the single level case, people have shown that you can get 1/epsilon⁵, but by using this stronger assumption. But under the classical assumption, even for the single level case, you can get 1/epsilon⁴. And here I showed that no matter of how many objective functions you have in the nested structure, you can still recover that 1/epsilon⁴ sample complexity. Yeah, I think this is pretty much what I wanted to discuss today. Thank you. And I welcome if you have any questions.
Okay, great. Thank you, Saeed, for the talk. Let me see. I don't see questions on chat, but please feel free to ask any questions you have now.
Hey, just a quick question.
Yeah.
If you do like the silliest thing and do like sample average approximation or ERM, does this converge asymptotically in the number of samples to the right thing?
You mean for the nested problem, right?
Yeah, so I mean like, take T samples, estimate the derivatives using the sample average approximation and solve this problem.
Yeah, so there are two issues. So first of all, we don't know how the bias term for the stochastic gradient is bounded in that case for the nested structure. Actually, one generalization of this case is, so here I assume that there is no dependence between the random vectors on each level. But for example, you can assume that there is a dependence between the random vectors, then this method does not converge. But I have seen that people have used this idea that you use this sample average approximation per iteration. And so example, sample the value of the inner function, use another mini batch to sample the stochastic gradient, and have shown convergence of that one, but you get a worse complexity bound.
Right. Sorry, that's not the question I'm asking. What I'm asking is if you estimate each of the stochastic functions using the average, fix this for T samples. This is now a deterministic function.
Yeah.
Gradients we have access to. Just solve this minimization problem. In the limit, as the number of samples goes off to infinity, does this converge to a solution to the original nested stochastic approximation problem?
So there is a work here by, let me see, where was this? Yeah. So here people have shown.
Yeah, so the center limit there.
Yeah, no matter of how many functions you have, the D-sample empirical optimal solution converges to the true optimal with the same rate. But the point is, asymptotic. Yeah, I mean, the point is this is the convergence of the optimal solution to the true value. But I don't know if you just solve that one, how close is the solution of that problem to the solution of the original problem?
Right, this exactly answers my question. Thanks.
Yeah.
Other questions? If not, maybe I have a question. Saeed, can you comment about the Oracle model you assume, and like in terms of what gradient, the assumption and the gradient Oracle, and in terms of kind of the motivating examples you had at the beginning, for example, the reinforcement learning problem, like how would they fit into this Oracle model?
Yeah, so here, so in all of those examples, I think the common assumption is to have unbiased estimator. For example, you have a matrix, you just want to sample, you get an unbiased estimator of that one, you just sample from that one. So I think this, so here I just have two assumptions. Having the unbiased estimator for the problem that, for the random quantity that you have, and assuming that either the variance or the second moment is bounded. For example, for many of the sub-Gaussian distributions, I think this second boundedness of the second moment is something that you can easily ensure.
And if you don't have like a first order Oracle, like you just have function evaluations?
Yeah, okay. Yeah, good question. So yeah, we have also worked on the zeroth order case that you just have the function evaluations. So for the two-level case, you can still get the same complexity bound. I mean, for sure you have the appearance of the problem dimension in the convergence rate, but still the convergence is 1 over epsilon to 4, but we are working on the case of the multi-level case, that what we can get out of it if you just have the function evaluations.
Okay, thank you.
You're welcome.
Okay, well, thank you all for coming. And thank you so much, Saeed. It was a fantastic talk.
Thank you. Thanks again for the invitation.
Thank you.
Bye-bye.
Have a good day. Bye.